So in the last class, we saw the functions and then their implementation using gates, AOI gates. Right? We saw different theorems also, Boolean theorems. Today what we will see is, we will see how these and NAND and NOR gates are used as universal gates. What do you mean by universal gates is a gate that can be used to implement any other functions are called as universal gates. Why you should use NAND and NOR as universal gates is because if you are able to implement any function that you normally use it using AND or not, only with NAND you are using only one kind of ICs, which is a NAND IC. Whereas if you are using AOI gates, you will be using an IC with AND operation, an IC with OR operation, and IC with NOT operation. Even if you, in case you are using an XOR gate, then you will use different IC. Each IC will cost differently, and at the same time there will be lot of unused gates inside those ICs also, which you will not be implementing for your actual functions. So those ICs are, in fact, will just occupy the space inside your ICs. So that is why if you see here, it is mentioned that the basic gates which are AND or NOT, when you use it with the help of NAND and NOR, these NAND and NOR will become really economical because you are using only one kind of ICs. And at the same time, since you are using different configurations in case of AND, OR and NOT, you will have to bias the transistors inside these gates actually. Now if you recall the TTL implementation of an AND gate, or even the diode logic implementation of AND gate or OR gates, you will see that those transistors needs to be biased. So biasing voltage will vary. When you have so many number of gates, what will happen is biasing has to be proper, and you will get lot of delays also. But whereas if you are using only one kind of a gate here, then they will be self-sufficient. Self-sufficient in the sense, one normal biasing is required, where all the NAND gates or NOR gates will operate in the active regions, or in whatever the regions, not in the active region, in whatever the region that is required. So hence, if you look at the gates and or not, they are used for simple circuit implementations. Whereas the XOR gate, they are used for parity generations. What do you mean by parity generation is, you just studied odd parity and even parity, right? How are those circuits that are generated? Say for example, you just studied a Hamming code where your parity bit P1 will check for an, if it's an even parity or an odd parity, you will check for even number of ones or odd number of ones respectively. Somebody asked, why are we studying this XOR gate as an odd function gate, right? If you remember, we explained this XOR gate, that this XOR implementation, these XOR functions are also called as an odd functions. Now, why this is an odd function? Because they are very, very helpful in having the odd parity generations. So that is why this XOR, we introduced this XOR as an odd function gates also. Now let us move on to using the NAND gates as the other gates. Now what is a NOT gate? What is a NOT gate is, say for example, if I have A, then the output of a NOT gate, if I am giving A as an input, then my output will be A bar. Okay. If you look at the truth table of a NAND gate, so A and B, the whole bar is the truth table of a NAND gate. So 0, 0, 0, 1, 1 0 1 1. The output will be 1 1 1 and 0. So for the same inputs, when both the inputs are same 0 0 and 1 1, you could see here that 0 becomes 1 and 1 becomes 0. Hence, this can be implemented, this function can be implemented by just using a NAND gate by combining both the inputs like this. So this can be given as A and this can be as A bar. Similarly, OR gates also. In case you want to implement an OR gate, so what is the Boolean expression for an OR gate? So if Z is the output here, OR gate is given as A plus B with two variables A and B as its input. Now if you want to convert this to an AND gate, what is the logic is you will have to apply De Morgan's law. How this can be written as A plus B, the double bar, right? Complement of a complement doesn't change the value, right? Now you apply De Morgan's law. This becomes, I'm going to break the inner line and change the sign. So this will become A bar dot B bar, right? I have broken the inner line and I will retain the outer line as it is, right? Now this has become an AND gate. How? If A is my input and B is my other input, first I have to create A bar, right? So what is A bar? A bar can be written as just as a NOT gate. This will be my A bar, right? So this is going to be my A bar. Similarly, my B bar will be this B bar. Now I have this A bar and B bar, and this too has to be ANDed and the whole bar must be there. Which means that an AND operation, if you consider this A bar to be say some X and B bar to be some Y, then it is nothing but X dot Y the whole bar, which is nothing but a simple implementation of an NAND gate. So combiningly, so this becomes A bar dot B bar and the whole bar. This is nothing but equivalent to an OR gate only, right? So this is how you implement NAND gate as a OR gate. Now, simple immediate question is, okay, OR is done. What about the AND operation? What about the AND gate implementation using NAND gate? Now, what is the AND? How is the AND gate given in terms of Boolean expression? It is given as A dot B. Again, let us apply the complement of a complement will give you the same thing, right? So if I make one complement, it is nothing but the NAND NOT gate implementation, and you make one more bar, complement of a complement, it doesn't change the value. So what we do here is we connect it to a NAND gate A dot B, right? So what will be this output? This output will be A dot B and the NAND gate operation. And then the NOT of this will become A dot B bar, the whole bar, the NOT of this. So this is nothing but A dot B, so which is an AND gate implementation. You might wonder, we are using one single gate for an OR implementation, right? So this is one single gate, but here we are using three gates. Here you are using again one AND gate only we will be using, but we are using two gates. Please note that it is not only the gates that is important, it is the IC that you are going to use here. You will be using only one IC to implement this function. And inside this one IC, you will have at least 4 different gates based on the number of inputs. So here, you will be using one IC only, but you will be using one gate. Here you are using one gate only, you will be using an AND gate. But in a circuit where AND, OR, NOT, XOR, all the functions are available, when you implement using the NAND gates, then you will be using only one kind of ICs there, whereas in these cases you will be using multiple different kinds of ICs and you will have to bias them properly also. My system got and yeah, okay, now it's working. So this is how you will implement using the uh, AND gate using NAND operation. Now comes the XOR gate. So certain books will have different way of representing. How is XOR gate given as? If Z is the output, XOR gate, the Boolean expression is going to be A bar B plus A B bar. Okay. Now, how do you convert this to NAND gate? Again, immediately whenever you want to convert this to NAND gate, you apply complement of a complement rule. So you make double complement. Now, when you always remember that your objective is to break the plus sign, not the dot sign. Okay. So this can be written as, if I break the inner bar, this will become A bar B the whole bar dot A B bar the whole bar. I have broken this line. I have broken this line, this bar, and then I will retain the outer bar as it is. Okay. Now I will have to implement this particular part. First is A. This will become A bar, right? This is A bar. Now I have B, and making this an AND gate, this will be A bar B the whole bar, right? Now, so I have made this particular part. This one A I can take it from here. B, I will create one more NAND gate from this. Sorry. So this will become B bar, and I want A here. So this becomes A B bar. Okay. And then the NAND of this. NAND of this will become A bar B the whole bar and A dot B bar the whole bar, which is nothing but the given expression, and which is nothing but the XOR value. Okay. So this is how you convert any given gate to a NAND gate. Any doubt here? Okay. It is the same implementation in fact. Now let us use NOR gate operation. Again for NOR gate also the rule is the same, but you must remember that here you are disturbing the plus sign here. Here you are disturbing the plus sign here. Similarly, when you are trying to implement using the NAND gate using OR gate, you wanted to remove this plus sign. That was your objective when implementing using NAND gate. Now, when implementing using NOR gate, you must disturb the AND sign here. Okay, so now let us make. So, how can you implement a NOT gate? So, NOT gate means I have a NOT gate here, A and A bar. Again, if you look at the truth table here for A, B, and for the NOR implementation, A plus B, the whole bar 0, 0, 0, 1, 1, 0, and 1, 1. A plus B, here it will be 1, 0, 0, and 0. Okay. Now, again, you see here that the same values 0 0 you will get 1, 1 1 you will get 0. So which means the NOT gate implementation using NOR gate can also be affected by using a NOR operation like this A, and this will become A bar. Now let's take the AND operation. Let Z equal to A dot B. We have to convert this into NOR gate. How do you do? This can be written as, again applying De Morgan's law, complement of a complement. Now your objective is to remove the dot signs. So this will become, break the inner bar, this will become A bar plus B bar the whole bar. So the same implementation can be done as A bar can be written like this. A bar. Similarly, B bar can be written as this to be B bar. This output will become A bar plus B bar and the not output. Okay. Any doubt here? Okay. So likewise, the OR operation. OR operation is, okay, system is hanging. Okay. So OR operation will be, you want A plus B only, you make double complement of it. So A plus B, the whole bar will be one OR gate here, and then you take one more NOR gate here, so it will be A plus B bar the double bar. Now let's implement using the XOR gate. So what is the XOR expression? XOR expression will be A bar B plus A B bar. Now I have already said, when you try to implement using NAND gate, you wanted to remove this plus sign, right? Here you must remove the dot sign that is present here and here. So what you should do is, again, you first make the complement of a complement rule, B bar, the double bar. Okay. Now the issue here is, if you apply this particular rule of double bar and double bar, when you break the bar, definitely you have to change this plus sign. So this is not a good method. Then what you should do? Instead, you apply the bar individually to the product term. You apply double bar to this plus A B bar. You apply double bar to this. Now this will become A bar will become A bar only. Let me do that later. B bar plus A bar plus B. It will become. Any doubt in this? Right? Still, this is an OR operation. So if you want to convert this into an OR operation, all you need to do is create double bar. Okay, so this will become implementing using a NOR gate. So that is how you do it. So this is the rule that I said you. Split this internal term. Instead of applying the whole bar outside, you must apply the double bar to this particular term separately, and then you will have to implement it. Okay. All right. So this is the complete XOR gate implementation. It's slightly uh, it depends on how you apply. If you can, it doesn't mean that you will end up wrong. You will also end up right, but the number of gates that are required will be very large. So you see here, the method of applying double bar has been used here. So whatever it will become, here it is. So yeah, so first you will have to apply some kind of a boolean expression here, and then the double bar implementation has been done. Okay. All right. Now next let's move on to the logic. What do you mean by, there are two different types of logics? One is called as a positive logic and other is a negative logic. What do you mean by positive logic? Is, in positive logic we will consider that 0 to be low, 0 to be low and 1 to be high. When we say high, it is normal voltage is 5 volts, and when we say 0, it is normal voltage is 0. In case of a negative logic, we say that high will be 0 and low will be 1. Okay. Now, if you have a digital circuit, if you want to activate this particular digital circuit, so this is a digital circuit. Okay. If you want to activate this digital circuit, normally we will give an external signal called as an enable signal. This enable signal, if it is a positive logic, we will write it like this. But if it is a negative logic, we will have to give a complemented input to activate this, which means that the whole digital circuit here will get activated only when you give a zero input across the enable signal. Okay, which means that all other time, if you are giving a high input, that is when E is equal to 1 volt or for plus 5 volts, then this digital circuit will not be active. Right. So here again, 0, in case of a positive logic, 0 is disabled by default, whereas 1 will enable your circuit. When we say 1, it means that it is an high, active high. What do you mean by active high is, it is normally 0, which is by default. If you want to enable it, we make it as 1 here. So this is how we represent our active high circuit as. Normally 1 is disabled, which means that normally 1, this will, under this circumstance, your circuit will be disabled. If you want to enable the circuit, then you have to give 0. So this is an active low circuit. Your gates, either they can be a active high circuits or it can be an active low circuit. Normally active low circuits are preferred than active high circuit. Active high circuits are preferred, that is the positive logic is preferred when compared to negative logics. Only on circumstances, important circumstances, we will use negative logics. Otherwise, we will be using positive logics. Now, if you consider gates, what is the circuit symbol is? For a NOT gate, you know that we are representing a triangle like this and then a bubble. Either you can use this way or even you can use this way also. But the IEEE standard, what it says is, it also says that you can use a square box with 1 written inside it. And then if it is a NOT gate, then you create a cross line like this. So this is a NOT gate. This represents the bubble. This represents the bubble. Similarly, you can have a bubble like this also, as mentioned in this particular diagram. This particular part denotes the polarity, right? This denotes the polarity. So these rectangular symbols can also be used as the gate symbols, especially for the NOT gates and gates. So the negation indicator, which is nothing but a bubble, represents the complemented form. We have seen this multiple number of times. Always your inputs will be on the left hand side and your outputs will be on the right hand side. Okay. Now, in case if a bubble is towards the input side, then it means that you are giving a complemented input. If you are giving A, then at this particular point, your input is going to be A bar. And your output now will be A. Sorry, yeah, A bar, and then the output will become A bar here. Whereas here, the input, if it is A, at this particular point, still it is A, only after the bubble here, it will be A bar. Okay. So the bubbling is very important here. A bubble on input side means that a 0 is active. Okay. Or asserted input state, and input is called as an active low input. So if you have a 0 here, where if your input is A bar, then it means that it is an active low input. Similarly, if a bubble is outside, then we call that as an active low output, in fact. Active low output. If there no bubble means, it means that 1 is active. You look at the NAND logic. This is your input side is an active high input because there is no bubble on the front side, on the input side. Here, the output, since the bubble is on the output side, it is an active low output, right? So active low output, whereas this is an active low input, active high input. The same circuit, the NAND gate, can be represented as a negative OR logic also. What do you mean by that is, you have an OR gate, you create a bubble here. This particular circuit is equivalent to a NAND gate. I will explain you later now. So these kind of inputs, since the bubble is inside, these are called as active low inputs, and your output is called as active high output. Okay, and it depends on the situation where you will use active high or active low inputs. Let us just verify the this circuit and the negative OR circuit, whether they are same or not. This can be easily verified by using the truth table. Let us quickly do that. What is that we are trying to do here is, we are having A, B. Let us write A bar and B bar. We want AB, the whole bar, which is nothing but a NAND circuit, and we want A bar plus B bar. Obviously, these both are same, right? Because these two equations, they satisfy the De Morgan's law. You break the line and change the sign, you will get this. Okay. Or you put one more double bar, you will still get this particular thing. Join the line and change the sign. So that is also right. So 0 0 0 1 1 0 1 1. So what is the complement of A? This is going to be 1 1 0 0. Complement of B is going to be 1 0 1 0. What is uh, A bar plus B bar? This is going to be 1 1 1 0. What is A dot B the whole bar? This is going to be 1 1 1 0. So both are equivalent, which means that NAND circuit here is equivalent to a complemented OR circuit, which is equivalent to a complemented OR circuit. This is true even for the otherwise also. That is, complemented AND circuit is equivalent to a NOR circuit, right? So that is what is mentioned here. An OR circuit is equivalent to a complement negative AND circuit. Okay, it's simple by applying the De Morgan's rule, right? You break the line here, so this x plus y the whole bar will become x bar dot y bar, which is nothing but a complemented input of x and y to an AND gate, which is this particular one. Now coming to the standard forms of representation of various things, we are going to define our different variables, and then we are going to use some technical terms here. Now what do you mean by standard form is, standard form of representing the Boolean expressions. There are two different standard forms of representing the Boolean expressions. One is called as the sum of products terms, shortly it is called as SOP. Similarly, the other is called as the product of sum terms, shortly called as POS. Now before moving into what is SOP and what is POS, first let us understand small terms, and then let us build on to the SOP and POS. What do you mean by literal? Every time we used to write, when we write a Boolean expression, say for example x plus x y bar, this is a Boolean expression. Every time I have been telling that there are these as variables, right? That is, what are the variables here? X is a variable and y is a variable, right? Now, these variables, along with its complemented form, they are called as literals. What do you mean by that is, if you want to verify this Boolean expression using a truth table, what do? You write list the variables on the input side, and then you will put all the combinations, right? 0 0 1 0 1 1 1 0 1, etc., right? All these combinations for these variables, they are called as literals. So define it properly. A variable on its own or in a complemented form, they are called as literals. Say for example x bar, y bar. These are called as literals. Now, what is a product term? The and terms are called as product terms. If I have two literals, say x and y are the two literals, x dot y is an and product term, x dot y bar is a product term, x bar dot y is a product term, x bar dot y bar, sorry, y bar is a product term. Okay, if I have three variables, then I will have z also. I will have z combinations. I will have 7 different combinations, and these are called as and term or product term. Now, what is the sum term? Similarly, the logic is the same. So, if I have two variables, x plus y is a sum term, x bar plus y is a sum term, x plus y bar is a sum term, x bar plus y bar is a sum term. Okay. Now, what will happen to a single literal? If I have a literal as x, does it qualify for a sum term or a product term? A single literal will qualify for both sum term as well as for a product term. Why? Because x can be, if it needs to be represented as a product term, then this can always be written as x dot 1. This x can be written as a sum term. Why? Because this can always be written as x plus 0 logic 0 term. So hence, a single literal terms can always be represented both as sum term as well as product terms. Now, what is sum of products? A sum of product is a product of, sum of all the product term means, some example here is x plus y plus. So this is a one product term and term. This is one and term and their sum. Similarly, one product term, second product term and their sum. Next, what is the product of sum term? This is one sum term, this is one sum term and their product. A sum term and another sum terms and their product. That is what is called as a product pos term. Any Boolean expression can be expressed as either as a sum or a product term expression. Okay, so this is actually a very powerful way of representing your Boolean expressions. Why? Because is only if you want to simplify an expression something like this, maybe one more something like this, then only if you represent as a sum of product or even as a product of some term, you can simplify these particular expressions in a standard form. I'll tell you the powerful way of simplifying this once we complete different terms here. Now let's define another term which is called as a min term. Min term, the other name is called as a minimum term. It's called as the min term. Right? Now, to understand min term, first you must understand, let us assume that you have two literals or two variables x and y. If x and y are the two variables, what are its literals that are possible? Please note, literals means the complemented and uncomplemented term of the variables are called as literals. So x is one literal, x bar is one literal, y is one literal and y bar is another literal. Now, if you have a min term with just two variables, then the combination of these literals, all four, how many literals are here? There are four literals are here. So four different possible combinations of these literals are called as min term. So what are the four different possible of these variables? X bar y bar is a product term, is a min term. X bar y is a min term. X y bar is a min term. X y is a min term. That is all these combinations not x bar, with only with the opposite variables x y and x y bar, x bar y and x bar y bar. All these are called as min terms. Okay, these product terms, they are called as min terms. Now, if you have n number of variables, then how many min terms are possible? There are 2 power n minterms are possible. It means that if I have two variables, then 0, 0, 0, 1, 1, 0 and 1, 1, which means that 2 power 2, which is 4 combinations are possible, right? Which means that 4 minterms are possible. If I have three different variables, then 8 minterms are possible. Okay. Alright. Now, what is a max term? Max term means if you have n different variables, here you use the product terms, right? In case of a min term, you use the product terms. X bar dot y bar, x bar dot y, x y bar and xy. These are product terms. If you use an OR term of these combinations of literals, then they are called as max terms. What do you mean by that is, say as an example of with two variables x and y, x bar plus y bar is a max term. X bar plus y is a max term. X plus y bar is a max term and x plus y is a max term. Again, how many max terms are possible if you have n variables? 2 power n possible combinations of max terms are possible. Normally, min terms are represented as small m. Min terms are represented as small m and max terms are represented as capital M. Now let me list you a table here. Okay. So, okay. So if I have two values x, okay, let me use the already presented. So let us assume that the three variables are x, y and z. Okay. So I think I should write. So if I have three variables x, y and z. Now what is the min terms that are available are? So the min terms, and let me give you the terms here and the way of notation. I will have to create a table. So what are the possible combinations here? The possible combinations are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1 and etc. I will complete this later. And how do you write the minterms is 0 corresponds to x, right? So the minterms that I will write is x bar, y bar. It is, please note, minterms are logic and terms, and z bar. This is the minterm. And how do I write the second minterm? It is x bar, y bar. It is z. X bar, y, z bar, x bar, y, z. These are all minterms. And how do I denote this minterm is, I'll write it as small m, and since the decimal equivalent corresponding to 0, 0, 0 is 0, so I write the minterm as m0. This one corresponds to m1, this one corresponds to m2 and m3. These are the minterms. Now coming to the max term, how am I going to represent the terms and notations are? Please note that your max terms, they are logic OR terms. So your 0, 0, 0, please note there's a very drastic difference here. The 0, 0, 0 will be represented as x plus y plus z, not x bar plus y bar plus z bar. Okay. And similarly, 0, 0, 1 will be represented as x plus y plus z bar. Please look at the difference. 0, 1, 0 will be written as x plus y bar plus z. Okay. And 0, 1, 1 will be written as x plus y bar plus z bar. And how do I represent the max term? I'll write it as capital M, and 0, 0, 0 corresponds to 0, m0, m1, m2 and m3. Now obviously when you are having a different Boolean expressions, you will have only these expressions. You will have only these expressions and you will not have the decimal equivalent. So your brain must calculate reverse. Though this looks like 111, you must assume that this is 000. These are logic zeros. So I'll give you the complete table here. So you see here, I'll take random example 101. Systems. Okay. So right, 101. The min terms are x bar y, sorry, x y bar z. X y bar z is the min term. Small m5 is how we represent in terms of min term. And don't look at this side, right? So what will be the max term? The max term will be 1 is represented as x bar plus 0 is represented as y and z bar, right? So this is the max term. And how do we represent the max term? It is m5. I'll just give you a random example. How do you represent x bar y z plus w bar in terms of max term, right? Please note that this is equivalent to, it's not equivalent to, I am just, for my calculation I am just writing, this is equivalent to 1001, right? So what is 1001 corresponds to 9. So this max term is equivalent to m9. How did I write 1001? I complemented this value. This is actually 0110, right? I complemented all the terms here, which came out to be 1009, and its decimal equivalent is 9. So the max term of this is m9. Okay. So and you must, how do you convert a min term to a max term? Min term to a max term conversion is fairly very simple because you have to apply just De Morgan's law. Let's take this one. Let's take this and this. How do you convert this min term to this max term? X bar, y and z, right? Take, apply De Morgan's law. So what is the De Morgan's law? Change the sign and then uh, break the bar, right? So x bar becomes x, y becomes y bar, and z becomes z bar, right? And dots becomes plus, and you got the same thing, right? X plus y bar plus z bar. Similarly, the reverse is also true, right? If say for example, I write a max term something like a bar plus b plus c plus d bar plus e bar, right? So this is a max term. If I want to convert this into a min term, then it is a dot b bar dot c bar dot d dot e, which is equivalent to 10011, right? So this is how you convert a max term to min terms and min terms to max terms. Any doubts here? Okay. So, as I said, if you want to convert, in case of a min term, 0 corresponds to logic 0 and 1 corresponds to logic 1 in case of min terms. In case of max terms, 0 corresponds to logic high and 1 corresponds to logic 0 in terms of max terms. And as just I showed you, a min term is a complemented form of the corresponding max term. If you want to convert this min term to a max term, all you need to do is complement and change the sign. So x bar will become x and dot will become plus, y bar will become y bar, dot will become plus, and z bar will become z. So this is the complement, this is the max term of the given min term. Okay. Any doubts? Okay. So I think it's 2:50. We can stop here. We will continue this min terms and max terms and even the logic zeros, say implementation using Nand terms in the next class. Any doubts? Okay. So if there are no doubts, then you may leave the class.